In this video, we are going to examine factors that affect strength of an acid. After completing it, you should be able to structure of a compound to its acid strength, and from structure of a molecule, you should be able to estimate how strong an acid it is. So the acid strength is an ability of particular compound to donate proton. So strong acids have very high tendency to donate protons and to protonate other compounds, other bases. So in case of reaction of strong acid with a base, a weak conjugate acid base is formed, conjugate acid base pair is formed, and equilibrium is to the right. The reason behind that is that conjugate base of the starting strong acid is stable conjugate base. As stable species, it has no tendency to react, and that makes the whole process favorable. On the other hand, weak acid, upon reaction with the base, gives conjugate acid-base pair in which conjugate base is unstable. So weak acid actually gives rise to strong conjugate base, unstable conjugate base. That unstable species has high tendency to react. Of course, if a species is a base, it means that its tendency is to accept a proton. And in that case, unstable conjugate base means strong base, therefore high tendency to accept a proton and reacts to give starting acid. So in this case, equilibrium will be to the left. So we can use some more relevant examples. For example, hydronium ion is strong acid, and in a reaction with a typical base, it gives stable conjugate base molecule of water. Molecule of water is obviously stable. You know how stable it is. It's compound that exists under ordinary conditions and is not that reactive. And of course, has relatively low tendency to accept a proton to give strong acid. On the other hand, molecule of water is weak acid. Its tendency to donate proton is relatively low, because the product is unstable conjugate base, hydroxide anion. Hydroxide anion is strong base. It has very high tendency to accept a proton and actually react in reverse reaction to give molecule of water. So in this case, spontaneous reaction would be from right to left towards water. Factors that affect acid strength are electronegativity of the atom or group attached to acidic hydrogen, hybridization of that atom attached to the acidic hydrogen, size of the atom attached to the acidic hydrogen, and then two of the electronic effects that more or less affect the entire molecule. And they are inductive effect and electron delocalization or resonance. We are going to examine each of these effects in detail and in the order in which they are listed here. Electronegativity of atom or group attached to acidic hydrogen plays a very important role in determining acid strength. Electronegativity is ability of atom or a group to attract shared electron pair. When atoms that are attached to acidic hydrogen are similar in size, then electronegativity plays a rather important role in strength of the corresponding acid. So since atoms should be similar in size, this is effect of electronegativity is best examined on example of atoms that are in the same period or same row of periodic table. So we should examine hydrides of the atoms of the same period of periodic table, and those would be hydrides of carbon, nitrogen, oxygen, and fluorine. And here we can see pKa values of the respective hydrides. So methane has pKa of about 50. It is not acidic at all. Removal of proton from methane really cannot be accomplished, and we don't have a base that would do that. So 50, here it says that pKa is about 50 because that's an estimate. To be able to determine pKa value, we need to establish equilibrium and determine position of the equilibrium. And here we can't even do that. Next, we have ammonia, and pKa is 36. That's very low pKa, that means extremely weak acid. Nonetheless, this proton can be removed by very strong base. Then we have water with pK of 15.7, and finally hydrogen fluoride with pK of 3.2. So we can see that acid strength increases from left to the right, and electronegativity of the atom bonded to hydrogen also increases in the same order. So electronegativity of carbon is 2.6, nitrogen 3, oxygen 3.4, and fluorine 4. So in this case, we can see that with increasing electronegativity, acid strength increases. The reason behind it is that upon deprotonation, more electronegative atom gives more stable conjugate base. So deprotonation of methane gives methyl anion. That's extremely unstable species. Carbon is very unstable in this form with negative charge and free electron pair, and will readily pick up any proton that is available around to form methane. Next we have amide anion. That one is slightly more stable, but actually amide anion is very strong base, extremely strong base, and actually is used, for example, in form of sodium amide as very strong base. Then hydroxide anion. Hydroxide is still strong base, but not nearly as strong as amide. And of course, strong means unstable. So the more unstable it is, the stronger base it is. More stable it is, weaker base. And finally, we have fluoride anion, very stable species. That's because fluoride is highly electronegative, and so it can tolerate negative charge and free electrons. So it's relatively weak base and has low tendency to accept a proton. So that's the effect of electronegativity. High electronegativity means that resulting conjugate base is going to be stable or weak base, and therefore starting acid will be strong acid. And from this you can draw a conclusion that strong acid gives rise to weak conjugate base, and conversely weak acid gives rise to strong conjugate base. Next effect that is related to electronegativity is hybridization. And hybridization is best examined on hydrides of the same element, of the atom of the same element that is of different hybridization. And since this is organic chemistry, of course, it is the best to examine carbon. So when we consider hydrocarbons, in which carbon is of different hybridization, we have just seen that methane has pKa of 50, and carbon is sp3 hybridized. Then we have ethene, where pKa is about 44. Again, very weak acid, but note this is logarithmic scale. So actually it's about, estimate is that it's about 1,000,000 times stronger acid than methane. That's a lot. And that's because carbon is sp2 hybridized. And finally, with sp hybridized carbon, we actually have reasonably strong acid for hydrocarbon. So this is ethyne or acetylene, where carbon is sp hybridized and pKa is 25. That actually can be deprotonated by some readily available bases. And so the effect of hybridization, of course, has to do with participation of orbitals in hybridization. sp3 hybrid orbital has 25% S character and 75% P character, so relatively low S character. sp2 hybrid orbital has much higher S character, 33% S character, 67% P character. And finally, sp orbital has the highest S character, 50% S character and 50% P character. That is important because when we consider atomic orbitals, S orbital is closer to the nucleus compared to a P orbital. P orbital, of course, has a node at the nucleus. And so by being closer to the nucleus, it experiences higher attraction. So electrons in S orbital experience higher attraction by the nucleus compared to those in P orbital. So atom of the same element that were to use S orbital for bonding will be much more electronegative, will much more strongly attract the shared electron pair if it uses S orbital for bonding than P orbital. And then, of course, we can extrapolate that to hybrid orbitals. If hybrid orbital has greater S character, it looks more like an S orbital, and therefore atom that utilizes sp orbital will be much more electronegative. compared to one that utilizes orbital with lower s character, such as sp2. And least electronegative would be atom that utilizes orbital that has lowest s character, which is sp3. So at the end, hybridization effect can be reduced to electronegativity effect. So we can consider that this is just a special case of electronegativity effect. With increased s character, electronegativity of atom increases and therefore acid strength increases. And conversely, of course, with increased electronegativity, corresponding conjugate base is more stable. So we can see that methyl anion is rather unstable. We have already seen that. And then this middle anion is called vinyl anion. It has intermediate stability because carbon is sp2 hybridized. And finally, the last anion is called acetylide anion. One that is from acetylene is called acetylide anion, and that one has the greatest stability. Effects of electronegativity and hybridization are important, but they play a major role only if atoms attached to acidic hydrogen are of similar size. If atoms have rather large differences in size, then atom size becomes more important. And we can see that on example of hydrofluoric and hydroiodic acids. So hydrofluoric acid upon dissociation gives rise to conjugate base, fluoride anion. This is small anion and charge is concentrated in small volume of space. Note first that there is negative charge and that there are 4 free electron pairs on fluorine. If they are concentrated in small volume of space, that means that there is a great deal of electrostatic repulsion. On the other hand, hydrogen iodide upon dissociation gives rise to iodide anion. Iodide anion is much larger than fluoride anion. And the difference is actually really huge. And so this is very large anion and it's much more stable. That's because first negative charge is diffused over a larger volume of space, and of course the 4 free electron pairs are diffused over a larger region of space. That means that electrostatic repulsion is much lower. It's considerably reduced. For that reason, iodide anion is much more stable compared to fluoride anion. And conversely, that means that iodide is much weaker base compared to fluoride anion. And then when we relate that to strength of the acid, that means that hydrogen iodide is going to be much stronger acid compared to hydrogen fluoride. And so when we compare hydrogen halides in terms of acid strength, we can see that pKa value of hydrogen fluoride is 3.2, hydrogen chloride -7, hydrogen bromide -9, and hydrogen iodide -10. This is opposite from the order of electronegativities because they are in the same group of periodic table and electronegativity decreases going down the group. So fluorine is the most electronegative while iodine is the least electronegative. So this is opposite from the order of electronegativities, and had we used electronegativity to predict acid strength here, we would have made a mistake. So we can see that atom size is more important and related to acid strength. So as we go down a group of periodic table, atom size increases and acid strength increases. So in this case, atom size plays more important role than electronegativity. And as I just explained, that's because with increasing atom size, corresponding conjugate base is more stable and therefore weaker base. So when you're comparing acid strength of 2 or more species across a row of periodic table or period of periodic table, you should compare electronegativities. Because if those atoms that form bond to hydrogen are in the same row, they have about same sizes. Then you should compare electronegativities to determine acid strength. But in a group, you should compare atom size. So if you're comparing species from the same group, atoms from the same group, compare atom size. Both atom size and electronegativity are periodic properties. Again, this is an abbreviated organic periodic table. So going across a period from left to right, atom size decreases and electronegativity increases. Going down the period, electronegativity decreases and atom size increases. There are 2 very important electronic effects that affect strength of the acids. Those are inductive effect and resonance effect or electron delocalization. So the first effect, inductive effect, is defined as displacement of electrons along sigma bonds. What that means is electron donation or electron withdrawal through sigma bonds. Now, it doesn't mean that electrons are completely donated or withdrawn through sigma bonds. This is only shift of electron density. So it's not that entire electron pair leaves sigma bond or is donated to one atom or the other. It's simply that electron density is shifted towards one atom of the bond or away from the other. So that's actually a consequence of the electronegativity effect. If two atoms of different electronegativities are bonded to each other, more electronegative atom will attract shared electron pair more strongly, and the electron pair or higher electron density will be closer to itself. It will develop partial negative charge, while the other atom will develop some partial electron deficiency and partial positive charge. Now that effect will actually propagate to the next bond, because now this partially positive atom, partial electron deficient, will tend to attract electrons it's sharing with other atoms and therefore affect neighboring bonds, and then those neighboring atoms in turn affect further atoms down the chain, and so that's how effect propagates through sigma bonds. So that would be inductive effect. And it does have considerable influence on strength of an acid. One way to examine it is on example of carboxylic acids that are substituted by halogen atoms. So we start with acetic acid as default acid that has no substituents, it has only hydrogens, and its pK value is 4.76. Now, if one of its carbon-hydrogen bonds is replaced with carbon-iodine bond, then pK value drops to 3.12, which is much stronger acid. So we can see that acid strength has increased. And then if instead of iodine, that substituent is bromine, acid is even stronger, 2.89, chlorine slightly stronger, 2.86, and fluorine the strongest, 2.66. So that's consequence of inductive effect. The way this effect works is that effect of halogen actually propagates through 4 bonds to affect oxygen-hydrogen bond and in turn acidity of the compound, acidic proton. So, for example, in case of fluoroacetic acid, resulting conjugate base is fluoroacetate anion, and it's much more stable compared to acetate anion because of the effect of fluorine atom. The effect, as I said, that spreads through 4 bonds. And here is how that effect works. Fluorine is much more electronegative than carbon. So it attracts electron pair it's sharing with carbon. It's partially negative, and carbon attached to fluorine is partially positive. So it's electron deficient. Being electron deficient, it now attracts electrons to compensate for its electron deficiency. It now attracts electrons it's sharing with carbonyl carbon, carbon that is part of carboxylic group. And so by sharing those electron pairs, it partially compensates for its electron deficiency. But now in turn that makes carbonyl carbon electron deficient. So that carbon, in order to compensate now for its electron deficiency, is going to attract electron pair it's sharing with oxygen, in this case negatively charged oxygen. And of course that's where the effect stops. We have reached the end of the chain. But consequence of all of it is that negative charge is not just localized on oxygen, which would make this oxygen somewhat unstable, but it's actually spread to 4 atoms. It's actually shared by oxygen, 2 carbons, and fluorine. And that makes the entire species much more stable because charge is spread throughout the molecule. And being more stable, it's weaker base. That means that starting acid is stronger acid. As you may expect, the magnitude of an inductive effect sharply decreases with distance of the substituent that is causing that effect and the reactive site, in this case OH group. So if we can examine that on series of chlorobutanoic acids. So butanoic acid has 4 carbons, and we can place chlorine substituent progressively further and further away from the OH group and examine its effect. So we can see that the closer the chlorine atom is to the carboxylic group, the stronger the effect is, or the stronger the acid is. And decrease, as you can see, is rather sharp. And when chlorine is on the 4th carbon, it's almost negligible. So you can see that butanoic acid has pK of 4.82. So 2-chlorobutanoic acid has pK of 2.84, pretty strong acid. But if we move chlorine to carbon 3, so 3-chlorobutanoic acid has pK of 4.06, much weaker. And 4-chlorobutanoic acid 452, almost negligible effect, almost the same as if there is no substituent. So as you can see, as effect spreads to 5 or 6 bonds, it becomes effectively negligible. Finally, inductive effects are additive, which means that effects of multiple substituents add up, and it's their sum that causes the overall inductive effect. Again, we can examine that on effect of chlorine and effect of chlorine on substituted acetic acids. So we can see that monochloroacetic acid has pK of 2.86 because there is effect of only one chlorine atom. Dichloroacetic acid has pK of 1.29. That's actually pretty strong. As far as organic acids go, that's actually rather strong acid and much stronger than monochloroacetic acid. So you can see that effect of 2 substituents is much stronger than 1. And finally, 3 substituents, trichloroacetic acid, pK is of 0.65, very strong acid, particularly for an organic acid. And we can compare that, of course, with acetic acid with pK of 4.76. Of all the effects that we have examined so far, were those of electronegative atoms. And of course, electronegative atoms are more, in general, non-metals are more electronegative than carbon, and so they increase acid strength. Electropositive atoms, such as, let's say, silicon or additional carbon substituents, will donate electron density to the carboxylic acid and actually make the carboxylic acid, or the corresponding base of the carboxylic acid, conjugate base of the carboxylic acid, less stable. So substituents that have lower electronegativity than carbon, what we call electropositive substituents, actually reduce strength of the acid. So remember, as a rule, that substituents that are more electronegative than carbon increase strength of the acid, and those that are less electronegative than carbon decrease strength of the acid. The other electronic effect that impacts acid strength is electron delocalization, or as you call it, resonance effect. Electron delocalization is a phenomenon, general phenomenon. It's displacement of electrons through pi bonds, and resonance is a method that we use to describe this effect in a valence bond theory. And valence bond theory is basically these formulas that we use in organic chemistry, like Lewis structures and various condensed and line formulas. So this is the effect that involves the localization of electrons or displacement of electrons through pi bonds. Nature is very similar to that of inductive effect. The difference is, of course, that inductive effect operates through sigma bonds, while resonance effect operates through pi bonds. And we can see how this effect operates on example of acetic acid. Acetic acid has pKa of 4.76, while ethanol, relatively similar compound, apparently structurally similar compound, pKa of 15.9. In each case, it's hydrogen that is attached to oxygen, that is acidic hydrogen, and both compounds have only 2 carbon atoms. The only difference is that acetic acid has carbonyl group, while ethanol has methylene or CH2 instead of carbonyl. And yet difference in acidity is more than 10 pK values. And since this is logarithmic scale, so that's really huge difference. Obviously, carbonyl group has inductive effect. It exhibits inductive effect we just covered. So carbon attached to carbonyl oxygen is electron deficient, and in turn it will withdraw electrons from oxygen, from negatively charged oxygen of the conjugate base, and stabilize it that way. So part of the acidity difference can be explained by inductive effect of the carbonyl carbon. But that cannot explain almost 11 or about 11 difference of 11 pKa units. And actually calculations were done that explains about half. The other half is due to resonance effect, or electron delocalization through pi bonds. And here is how electron delocalization through pi bonds works. So the electron pair on oxygen is delocalized on oxygen of hydroxyl oxygen, is delocalized to form a partial double bond with carbon, and carbonyl oxygen pi electron pair is delocalized to partially belong to carbonyl oxygen. From this, from the formulas in the upper left corner, resonance forms of acetic acid, you can see that actually such compounds cannot be accurately represented with a single formula, with a single Lewis structure. So we actually have to use combination of Lewis structures and draw individual resonance forms. So to represent the electron delocalization, in this case we have to use two extreme forms. One is Lewis structure of acetic acid that you are used to, that you have seen how we represent it usually. And then second one is shown as shift of the electrons indicated by curved arrows. So what I just mentioned, movement of electron pair from oxygen to form double bond with carbon, and movement of pi electron pair from carbon-oxygen double bond to carbonyl-carbon. So that gives us second extreme structure, and that structure actually, as you can see, has charge separation. The actual structure of acetic acid is somewhere between the two. It's combination of the two. So neither structure accurately represents acetic acid, but the actual structure is combination of the two. You can see that as a result of it, oxygen that is attached to hydrogen develops partial positive charge and partial electron deficiency. Now, the effect is even more important in case of acetate anion, because in case of acetate anion, when we follow the same procedure, you can see that we end up with two equivalent structures. So electron delocalization results in two equivalent resonance structures, and each of the oxygens now carries half the negative charge. In fact, we cannot really distinguish two oxygens. We cannot tell which one is negatively charged oxygen, which one is carbonyl oxygen. So negative charge is delocalized. Each oxygen actually carries half the negative charge, and each carbon-oxygen bond is effectively half a double bond, so 1.5 the bond. That makes acetate anion very stable because charge is delocalized and electrons are delocalized. That minimizes electrostatic repulsion and makes resulting anion very stable. And when resulting anion is stabilized through electron delocalization or resonance, then starting acid is much stronger acid than in the absence of resonance. We can draw some formula of acetic acid, like this one in the middle, that shows electron and charge delocalization acetate anion, where we show partial bonds and partial charges. Some students prefer that, but actually it's not very good representation. In general, you should stick to representing individual resonance structures and using double-headed arrow. So double-headed arrow is an indication that those are resonance structures and that the actual structure is the combination of the two, somewhere between the two. We can see that such stabilization is not available to molecule of ethanol. And so molecule of ethanol upon deprotonation gives only unstable ethoxide anion, and there is no possibility for delocalization of negative charge. So that's why it is much weaker acid. There are numerous examples of acid being rather strong as a result of electron delocalization or stronger, and they are both from inorganic and organic chemistry. So for example, sulfuric acid, an inorganic compound, is much stronger than one would expect because resulting anion is stabilized through resonance. In this case, we have 3 equivalent resonance structures, which renders resulting bisulfate anion rather stable. One good example from organic chemistry is that of molecule of phenol. Phenol is unexpectedly acidic because it should be just an alcohol, but actually its pK value is 10 as opposed to 16 for ordinary alcohol. And that's consequence of electron delocalization. So negative charge and electron density is delocalized over the benzene ring, resulting in 5 resonance structures, and that makes phenol much stronger acid. And so here we can list some common acids in the order of increasing strength. So Ethanol and cyclohexanol have about the same acid strength, same pK values of about 16. Cyclohexanol is included here because of its structural similarity to phenol. So that's one we should compare to phenol when comparing compounds with and without electron delocalization. So phenol with electron delocalization has pK value of 10, while cyclohexanol 16. So you can see how much stronger acid it is. And then carboxylic acids, which we have covered earlier, have pK values of between 4.5 and 5. And finally, sulfuric acid is rather strong inorganic acid and has much larger pK value. It's negative. I don't remember the number, but I think it's negative like 3 or 4. pK is minus 3 or 4. We'll briefly look at determination of base strength. To determine strength of a base, you should apply principles that you have learned in this video on determination of acid strength and simply apply that to base strength. So, for example, we have determined that an electron withdrawing substituent increases strength of an acid and electron donating substituent decreases strength of an acid. So conversely, one can conclude that an electron withdrawing substituent will decrease strength of a base and that electron donating substituent will increase strength of the base. So that effects will be opposite from that of effects to acids. And that's reasonable. A little bit of a problem with that is that electronic effects have relatively low importance when reactions of bases are carried out in solutions. Much more importance has to do with solvation of a base. How well base is solvated. Base that is very well solvated is weak base, poorly solvated base is strong base. But you have no way to determine that. Fortunately, a simple consideration of electronic effects, the way I just mentioned, will result in correct prediction. That's largely by coincidence, but nonetheless you will end up with correct result. So if you're taking exams, particularly standardized exams like MCAT or GRE or ACS exam, that's what test makers expect you to do. So the determination of base strength, you're expected to assume that electron donating substituent increases strength of a base and electron withdrawing substituent decreases strength of a base. So opposite from effect on the acids. Another way to determine base strength is from the strength of the corresponding acid. So for example, here we have 3 bases, and to determine strength or to arrange these 3 bases in the order of increasing or decreasing strength, we can look at the corresponding acids. So these are the acids HF, H2S, H3AS. So these 3 acids, we actually, using previous rule, they have diagonal relationship periodic table, so it's rather difficult to determine their relative acid strength. But we can look up their pK values, and they may be provided on the exam. So if their pK values are provided, we can see that HF is by far the strongest, pK 3.2, then H2S, pK 704 intermediate strength, and H3S very weak acid, pK 23. So we can arrange acids in the order of decreasing strength. HF strongest, H2S intermediate, H3S the weakest. Now we know that when we look at bases, those are conjugate bases of these 3 acids. And we know that conjugate base of a strong acid is weak base. Conjugate base of weak acid is strong base. So simply order will be reversed. Since HF is the strongest acid, F- is going to be the weakest base. And since H3S is the weakest acid, H2S- is going to be the strongest base. This completes our review of strength of the acids and bases and how to determine them. And in the next chapter, we'll be looking at theory of organic reactions.